Good morning to everyone. Myself, Vai Bharat. Today I am here to present my Tech Talk presentation. Today my topic is harmonics and torque. Introduction. Harmonics in inverter fed drive causes torques, ripple and performance degradation. This presentation summarizes primary source modeling approaches and analysis method to qualify and reduce torque pulsations. Focus on practical diagnostics and control oriented migration to improve reliable and efficiency in industry motor drives. Harmonic sources. Inverter switching pattern. PWM switching produces voltage and current harmonics in discrete frequency components. These harmonics interact with motor impedance, creating torque ripple at beat frequencies. Analyze switching scheme carries frequencies and modulation index to predict diminution harmonic orders and their impact. PMDL switching produces voltage and current harmonics with discrete frequencies components. These harmonics interact with motor impedances, creating torque ripple at beat frequencies. Analyze switching scheme carries frequencies and modulation index to predict domination harmonics orders and their impact. Supply and load distribution. Distortion supply voltage and nonlinear loads inject low and high order harmonics into the drive system, resulting asymmetric generate alternating torques components and increased vibration. Measure supply THD and perform spectrum analysis to identify corrective filtering or supply condition needs. Distort supply voltage and nonlinear loads inject low and high order harmonics into the driven system, resulting asymmetric generation alternating torque components and increased vibration. Measure supply THD and perform spectrum analysis to identify corrective filtering on supply conditions needs. Motor nonlinearities. Magnetic saturation, slotting, and parameter vibration creating additional harmonic torque components, mechanical resonances, and amplify small torque pulsations. Included nonlinear effects is models to capture phenomenon like cogging and modulation of electromagnetic torque. Include nonlinear effects in modeling to capture phenomena like cogging and modulation of electromagnetic torque. Modeling methods. Use harmonic impedance and steady state phasor methods to identify resonant interactions and domination harmonic orders. Efficient to flood and PMW design. Provide quick estimation to torque ripple amplitudes across frequency bands and for control tuning. Frequency domain analysis use harmonic impedance and steady state phasor methods to identify resonant interactions and dominate harmonic orders efficient for filtering and PMW design. Provide quick estimation or torque ripple amplitude across frequency bands for controlling tuning. Time domain simulations. Transient solutions, TP models, finite elements, time splitting, capture nonlinearity equations, switching transient and mechanical coupling essential for validating control strategies and worst case ripple scenario combined with exponential validation to ensure model fitness and implement migration measures. Transient solutions, DP models, finite elements, time sensing, capture nonlinearity, switching transient and mechanical coupling essential for validating control strategies and worst case ripple scenarios. Combined with experimental validation to ensure model fidelity and implement mitigation measures. Finite element modeling. Use 2D or 3D finite element simulations to capture Natural flux distribution, saturation, and slotting effect. Validate time shifted electromagnetic torque waveforms to predict local torque, pulsating, and mechanical coupling. Use 2D, 3D finite elements simulations to capture spectral flux distributions, saturation, and slotting effect. Validate time spent by electromagnetic torque waveforms to predict local torque pulsations and mechanical coupling. Mitigation techniques. Filter design approaches design passive LCL or attractive filters to attenuate dominant harmonics order at which inverter output. Evaluate filter impedances interaction with motor to avoid resonance and ensure stable suspension. Design passive LCL or attractive filters to attenuate dominant harmonic orders at inverter output. Evaluate fine impedance interaction with motor to avoid resonance and ensure stable suspension. PMW modeling strategies. Optimize PMW scheme SVPWM. Selective harmonics eliminations to minimize low order harmonics and switching beats. Adjust carriage frequencies and phase shift techniques for multi-level converters to reduce torque ripple components. Optimize PWM schemes PSPWM SVPWM sensitive harmonic eliminations to minimize low order harmonics and switching beats. Adjust carriage frequencies and phase shift techniques for multi-level converters to reduce torque ripple components. Control based components. Implement torque ripple feed forward and current shaping control in DP frame to cancel project distributions. Use adaptive observations or repetitive control to track and suspension predict harmonic torque components. Performance evaluation. Torque ripple quantities measure peak to peak and RMS ripple factors decompose into harmonic order 50. Report matrices per load and speed operation points to guide mitigation properties. Efficient losses assessment. Access additional losses for harmonic current, copper, iron, and switching losses. Balance ripple reflection benefits against filter control losses to optimize overall system efficiency. PWM and modulation strategies. Optimize PMW start scheme P SPWM SVPWM selective harmonic elevations to minimize low order harmonics and switching bits. Adjust carriage frequencies and phase shift techniques for multi level converters to reduce torque ripple components. Control based compensation. Implement torque ripple forward and current shaping controllers in the DP frame. Cancel periodic distributions. Use adaptive observations or repetitive control to track and suspend predict harmonic torque components. Torque ripple quantities measure peak to peak and RMS load ripple decompose into harmonic orders using FFTs. Report matrices per load and speed quantitating options to guide mitigation properties. Efficiency and losses. Access additional losses from harmonic current, copper, iron, and switching losses. Balanced ripple reduction benefits against filter control losses to optimize overall system efficiency. Experimental validation methods. Combine dynamometer test shaft torque sensors and motor side current spectra for comprehensive validation. Use synchronous averaging to isolate periodic torque components for noise and transient effect. Conclusion. Modeling FEM and time domain pulse target mitigation filters PMWs and control effective reduce harmonic induced torque ripple qualify ripple and validate experimental to ensure reliable efficient drive performances.